What is Big O notation and why does every developer need to understand it? When you write code that works correctly on a small dataset but slows to a crawl on a large one, the problem is almost always algorithmic efficiency. Big O notation is the universal language developers use to describe and compare how the performance of an algorithm changes as the size of its input grows. It does not measure exact execution time, which varies by hardware, but rather the rate of growth, which stays consistent regardless of the machine. O of 1 or constant time means the operation takes the same amount of time regardless of how large the input is. Accessing an element in an array by index or looking up a value in a hash map are O of 1 operations. These are the fastest possible algorithms. O of log n or logarithmic time means the operation gets slower as input grows, but very slowly. Each step cuts the remaining work in half. Binary search on a sorted array is the classic example. Searching through 1 billion elements takes only about 30 steps with a logarithmic algorithm. O of n or linear time means the operation scales directly with input size. Doubling the input doubles the time. Iterating through every element of an array once is O of n. This is usually acceptable for most real-world problems. O of n log n is the typical complexity of efficient sorting algorithms like merge sort and quick sort. It is the theoretical best case for comparison-based sorting and is fast enough for most practical sorting tasks. O of n squared or quadratic time means every element is compared to every other element. Nested loops over the same array produce O of n squared time. This is usually acceptable for small inputs, but becomes devastatingly slow as input grows. 1,000 elements means 1 million operations. 1 million elements means 1 trillion operations. O of 2 to the n or exponential time means the algorithm doubles in work with every additional input element. These algorithms become completely unusable even for moderately sized inputs and always need to be optimized using dynamic programming or memoization. When you analyze an algorithm, you drop constants and lower order terms because at very large inputs, only the dominant term matters. Understanding Big O lets you look at code and immediately know whether it will scale or collapse under real-world load. Follow DevVerseX for more daily interview questions to level up your career.